13.8 billion years ago, in the first 380,000 years after the Big Bang, the universe became transparent for the first time. Before this moment, space was so hot and dense that photons could not travel more than a tiny fraction of an inch before being absorbed and re-emitted. Then, suddenly, the cosmos cooled enough for light to fly free. Some of those primordial photons have been traveling ever since, carrying within them the temperature signature of the infant universe, the pattern of density fluctuations that would later become galaxies, the quantum memory of a time when matter and energy had barely separated. Tonight, some of those ancient photons, older than planets, older than stars, older than chemistry itself, will enter our telescopes. When we capture them, we are not just observing distant objects. We are reading light's memory, decoding information that has been perfectly preserved for longer than human minds can truly comprehend. Light is not simply what allows us to see. Light is what allows the universe to remember. And tonight, we discover why photons never forget. The nature of light's memory. Consider what it means for something to remember. In human consciousness, memory requires physical substrate. Neurons form connections, proteins fold into specific shapes, electrical patterns stabilize across neural networks. Memory has weight, quite literally. The act of remembering changes the mass of your brain by measurable amounts as molecules reorganize themselves to encode experience. But light has no such substrate. A photon has no internal structure we can observe, no moving parts, no mechanism for storage that makes sense in classical terms. Yet photons remember. They remember with perfect fidelity. They remember across distances so vast that the numbers lose meaning. A photon that left the Andromeda Galaxy 2.5 million years ago carries within its quantum state precise information about the star that emitted it. Not approximate information, not degraded information, perfect information, encoded in properties that have remained absolutely stable across a journey of 15 quintillion miles through the vacuum of space. How does something with zero rest mass carry the weight of memory? How does something traveling at the speed of light, experiencing no passage of time from its own reference frame, manage to preserve information about events that, from our perspective, occurred billions of years ago? The answer reveals something fundamental about the nature of reality itself. Information is not just recorded in matter. Information is a property of spacetime itself, and photons are the universe's way of moving that information from one location to another without loss, without degradation, without the entropy that destroys all other forms of memory. This is not metaphorical memory. This is literal information preservation across timescales that dwarf human history. The cosmic microwave background photons remember the precise state of the universe when it was 380,000 years old. They have carried this memory through epochs that saw the birth and death of entire generations of stars, through the formation of planets and the emergence of life, through all of human civilization from its beginning to this present moment. And the information has not degraded. It has not faded. It remains perfectly encoded, waiting to be read by anyone who knows how to listen. Light's memory at the quantum level is thus more subtle and profound than classical memory. It is not simply a recording of events. It is an entangled web of quantum correlations that preserve information about the complete history of all interactions the photon participated in. This information cannot be fully accessed by any single measurement, but it exists nonetheless, woven into the fabric of the wave function, waiting for observers clever enough to design experiments that can extract meaning from quantum correlations. While quantum mechanics describes the ultimate nature of light, electromagnetic field theory provides another lens for understanding how photons carry information. A photon is, after all, a quantum of electromagnetic field energy. It represents a localized excitation in the electromagnetic field that permeates all of space. When we talk about light traveling from a star to Earth, we are really describing how an electromagnetic disturbance propagates through the field at the speed of light. The electromagnetic field has two components, electric and magnetic, oscillating perpendicular to each other and perpendicular to the direction of propagation. These oscillations carry energy and momentum, but they also carry information about the source. The frequency of oscillation depends on the energy level transitions in atoms at the source. The polarization depends on the orientation of the electric field, which can be influenced by magnetic fields or scattering geometry. The phase relationship between different photons depends on the coherence of the emission process. What is fascinating is that electromagnetic fields can encode information in ways that seem impossible from a particle perspective. Interference patterns, for example, arise from the wave nature of light. When two light waves overlap, their electric fields add together. If the waves are in phase, peaks align with peaks, and the fields reinforce each other. If they are out of phase, peaks align with troughs and the fields cancel. This creates bright and dark fringes in space, patterns that encode information about the phase relationship between the sources of light. Holograms exploit this property to store three-dimensional information in two-dimensional patterns. A hologram is created by combining light reflected from an object with a reference beam. The interference pattern between these two beams is recorded on film or other media. When you illuminate the hologram with light similar to the reference beam, the recorded interference pattern diffracts the light to recreate the original wavefronts that came from the object. The result is a three-dimensional image that appears to float in space, reconstructed from the information stored in the interference pattern. What this tells us is that light can store information not just in individual photons, but in the relationships between photons, in the patterns formed by electromagnetic field interactions. This is a form of memory that has no classical analog. Information is not localized to a specific physical object. It is distributed across the structure of the field itself, existing in the correlations between different regions of space. This distributed memory is extraordinarily robust. You can destroy part of a hologram, and the remaining portion still contains information about the entire three-dimensional scene, just with less resolution. The information is holographic in nature, meaning every part contains information about the whole. This is very different from a photograph, where destroying part of the image destroys the information it contained. Light's memory, encoded in field patterns and interference, has a redundancy that makes it resistant to partial loss. Astronomers use this property when they perform interferometry, combining light from multiple telescopes to create interference patterns. These patterns contain more information about the source than any single telescope could capture. The technique has allowed us to image the surfaces of distant stars, resolve binary systems, even capture the shadow of a black hole. In each case, we are not simply collecting light. We are reading the information encoded in the electromagnetic field structure, in the phase relationships between photons arriving from different directions, in the interference patterns that reveal details far smaller than any single telescope could resolve. Despite its remarkable properties, light's memory has limits. These limits arise not from imperfection in photons themselves, but from the nature of information and the structure of spacetime. Understanding these limits helps us appreciate both the power and the boundaries of light as a memory medium. The first limit is spectral. A photon's energy is quantized, meaning it can only have specific discrete values determined by Planck's constant and its frequency. This quantization means that some information is inherently discrete rather than continuous. You cannot have half a photon. You cannot have a photon with energy between two allowed quantum levels. This discreteness limits the precision with which energy information can be encoded in individual photons. The second limit is spatial. Photons spread out as they travel. A beam of light expands, and the energy becomes distributed over a larger and larger area. This is why distant stars appear fainter than nearby stars. The photons have spread across an enormous sphere, and we intercept only a tiny fraction of them. The information is still there, encoded in all the photons, but most of them miss us entirely. They carry their memories off into directions we cannot access. The third limit is interference from the medium. Light traveling through matter or fields can be scattered, absorbed, or distorted. Interstellar dust absorbs and scatters light, especially blue wavelengths. Intergalactic plasma can disperse radio waves, causing different frequencies to arrive at slightly different times. Gravitational fields bend light, changing its direction and creating lensing effects. Each of these interactions modifies the information carried by photons, sometimes irreversibly. The fourth limit is quantum. Heisenberg's uncertainty principle means we cannot simultaneously know all properties of a photon with infinite precision. Measuring one property disturbs others. This is not a technological limitation. It is a fundamental feature of quantum mechanics. Information exists in the quantum state, but we cannot extract all of it without destroying the state itself. The fifth limit is cosmological. The expansion of the universe stretches light as it travels, shifting it to longer wavelengths and lower energies. This cosmological redshift is irreversible. A photon that started as ultraviolet light from a very distant galaxy might arrive at Earth as infrared or even microwave radiation. The information is preserved, but it is encoded in a different form. Extreme redshift can push photons to wavelengths so long that they become nearly undetectable, their information slipping below the threshold of measurement. Finally, there is the information horizon. Light can only carry information about events in its past light cone, the region of spacetime from which light could have reached its current position. Events outside this region remain forever unknown to that photon. As the universe expands, more and more of spacetime falls outside our observable horizon. Photons from those regions can never reach us. Their memories are lost, not because the information was destroyed, but because the geometry of spacetime prevents it from ever arriving. These limits remind us that light's memory, while remarkable, is not infinite or absolute. It is bounded by quantum mechanics, shaped by spacetime geometry, filtered by the matter and fields it encounters. Yet within these constraints, light remains the most reliable, most persistent, most faithful memory system the universe has created. No human technology, no biological mechanism, no physical process we know of preserves information as well as light does across cosmic distances and timescales. Before we explore entanglement, we must confront one of the deepest mysteries in physics. Light is both wave and particle, existing simultaneously as both until observation forces it to choose. This is not metaphor. It is not approximation. It is literal truth, verified by countless experiments over more than a century. The photon is wave. The photon is particle. The photon is both. The photon is neither. Which answer is correct depends on what question you ask, what measurement you perform, what aspect of reality you choose to observe. The famous double-slit experiment demonstrates this with stark clarity. Send photons one at a time toward a barrier with two narrow slits. Place a detector screen behind the barrier to record where each photon arrives. If you do not observe which slit the photon passes through, you will see an interference pattern emerge over time, alternating bands of light and dark exactly like water waves passing through two openings and creating regions of reinforcement and cancellation. This proves the photon behaved as a wave, passing through both slits simultaneously and interfering with itself. But if you place detectors at the slits to determine which path each photon takes, the interference pattern vanishes. You get two bright bands behind the slits, exactly what you would expect if photons were particles taking definite paths through one slit or the other. The wave nature disappears the moment you try to observe it. The universe will not let you see both aspects simultaneously. What makes this truly mysterious is that the choice to observe which path is taken can be made after the photon has already passed through the slits. Delayed choice experiments show that you can decide whether to measure path information or allow interference after the photon is already committed to its journey. Your future choice seems to reach back in time and determine whether the photon behaved as a wave or particle in the past. This is not time travel in any conventional sense. It is something stranger. The past is not fixed until observation brings it into definite existence. This suggests that light's memory is more subtle than classical intuition allows. The photon does not have a definite history until that history is observed. Before measurement, the photon exists in superposition, having taken all possible paths simultaneously. Information about which path was actually taken does not exist because the photon did not actually take any single path. It took all paths, and only when observed does one path become real while others fade into unrealized possibility. This has profound implications for understanding what information means in quantum mechanics. If the photon's history is indefinite until observed, how can we say it carries memory? What is being remembered if the past itself is not definite? The answer lies in recognizing that quantum memory is fundamentally different from classical memory. It is memory of possibilities, memory of superpositions, memory encoded in wave functions rather than definite states. The interference pattern is itself a form of memory. It encodes information about phase relationships between different paths the photon could have taken. This information exists in the probability amplitude, the complex number that describes the likelihood of finding the photon at each location. The probability amplitude carries phase information that cannot be reduced to classical probabilities. It is inherently quantum, requiring the full machinery of wave functions and superposition to describe properly. When we observe the photon and collapse its wave function, we lose access to this quantum information. The interference pattern disappears because observation forces the photon to choose a definite state, destroying the superposition that allowed multiple paths to coexist. The memory that was distributed across all possible paths collapses into memory of one actual path. Information is not destroyed in this process, but it is fundamentally transformed from quantum to classical form. This transformation is irreversible under normal circumstances. Once the wave function collapses, you cannot recover the quantum state that existed before. The information about phase relationships between different possibilities is lost, replaced by definite information about which possibility was actualized. This is why quantum information is so fragile. Any interaction with the environment can cause decoherence, collapsing superpositions and destroying quantum memory. Yet, in carefully controlled conditions, quantum superpositions can be maintained. Photons can be kept isolated from environmental interactions, preserving their wave-like nature and the quantum information encoded in their states. This is the basis for quantum computing and quantum cryptography. Information is encoded in superpositions that can process multiple possibilities simultaneously, providing computational advantages impossible with classical systems. Light's wave-particle duality thus reveals a deeper truth about memory and information. There are two kinds of memory, classical and quantum, and they are fundamentally different. Classical memory records definite facts about what happened. Quantum memory preserves superpositions of what might have happened, maintaining multiple possibilities in coherent parallel. Light can carry both kinds of memory depending on how we interact with it, how we choose to observe it, what questions we decide to ask. This flexibility is part of what makes light such a powerful memory medium. It can store information classically in properties like wavelength and intensity. It can store information quantumly in superpositions and phase relationships. It can preserve both kinds simultaneously until observation forces a choice. Light adapts to our needs, to our measurement strategies, to the questions we ask about reality. It is the ultimate information chameleon, shape-shifting between wave and particle, between definite and indefinite, between classical and quantum as circumstances require. Let us go deeper into interference, the phenomenon that most clearly reveals light's wave nature and provides some of its most remarkable memory capabilities. When two or more light waves overlap, they combine according to the principle of superposition. If the waves are in phase, their electric fields align and add together, creating brighter light. If they are out of phase, the fields oppose and cancel each other, creating darkness. This is interference, and it can encode and preserve information in ways that have no classical analog. Consider a hologram again, but now with fuller understanding of what it represents. When you create a hologram, you are recording an interference pattern between light reflected from an object and a reference beam. This pattern contains information about both the amplitude and phase of the reflected light at every point where the hologram will be recorded. Amplitude alone would give you a photograph. Phase adds a dimension that preserves three-dimensional information in a two-dimensional recording. The key is coherence. For interference to occur and persist, the light waves must maintain a definite phase relationship over time. This means they must be coherent, arising from the same source or from sources that are carefully synchronized. Coherent light preserves phase relationships over long distances and timescales, allowing interference patterns to remain stable and readable. Laser light is highly coherent. All the photons are in phase with each other, oscillating together like a perfectly synchronized chorus. This makes lasers ideal for creating holograms, for precision measurement using interferometry, for quantum communication using phase encoding. The coherence ensures that phase information is preserved reliably enough to be useful for technical applications. Natural light from stars is less coherent but not completely incoherent. Different atoms in a star's atmosphere emit photons independently, creating light with random phase relationships. Yet, over short timescales and within small spatial regions, some coherence persists. This residual coherence is what allows us to use interferometry in astronomy, combining light from multiple telescopes to achieve resolution far beyond any single telescope. The coherence of light is related to its spectral purity. Perfectly monochromatic light with a single wavelength would be perfectly coherent. Real light always has some spread of wavelengths, some bandwidth, and this limits coherence. The broader the spectrum, the shorter the coherence length, the distance over which phase relationships remain stable enough for interference. This connects to information theory in a beautiful way. The bandwidth of light determines how much information it can carry. A narrow bandwidth photon is highly coherent but carries less information because its properties are more predictable. A broad bandwidth photon can carry more information because its spectrum can encode more variation, but it is less coherent and cannot maintain interference over long distances. There is a trade-off between information capacity and coherence, between how much you can say and how clearly you can say it. Light from the cosmic microwave background has extremely narrow bandwidth, nearly monochromatic. These photons have been traveling for billions of years and remain highly coherent. They carry less information per photon than visible light, but what information they do carry is preserved with extraordinary fidelity. The temperature fluctuations we measure in the CMB are tiny, parts per 100,000, but they are real and significant because the coherence of microwave radiation allows us to measure them with great precision. Conversely, light from a rapidly changing source like a pulsar or a flickering flame has broader bandwidth and shorter coherence times. Each burst of light carries more information about the instantaneous state of the source, but that information is encoded in ways that are less stable, less persistent over long distances. The information is still there, but accessing it requires faster detectors and more sophisticated analysis techniques. Interference patterns themselves can store information in ways that are remarkably robust. The pattern encodes not just the average properties of light, but the correlations between different parts of the light field. You can destroy part of an interference pattern and still extract information about the whole because the correlations extend across the entire pattern. This is holographic in nature, with each part containing information about the whole at reduced resolution. This property has practical applications. Holographic data storage uses interference patterns in three-dimensional media to store enormous amounts of information in small volumes. The data is distributed throughout the medium such that local damage does not completely destroy any particular piece of information. Multiple holograms can be stored in the same volume by using different reference beam angles, creating a superposition of interference patterns that can be separately retrieved by illuminating with the appropriate reference beam. All of this relies on light's ability to interfere constructively and destructively based on phase relationships. These phase relationships are preserved by photons as they propagate, maintained by the coherence of the light, encoded in the quantum state of the electromagnetic field. When we use interference to store or transmit information, we are exploiting light's memory at the most fundamental level, using the preservation of phase to carry data that would be impossible to encode in intensity alone. There is one more aspect of light's memory that pushes the boundaries of our understanding. Quantum entanglement, Einstein's spooky action at a distance, allows photons to share information in ways that seem to violate our classical intuitions about locality and causality. When two photons are entangled, measuring a property of one photon instantly affects the state of the other, regardless of the distance between them. This correlation is not due to any signal traveling between the photons. It is a fundamental feature of quantum mechanics that defies simple explanation. Entangled photons can encode information in a fundamentally different way than classical systems. The information is not stored in the individual photons, but in the correlation between them. You cannot extract the information by measuring one photon alone. You must measure both photons and compare the results to see the correlation. This property makes entangled photons useful for quantum cryptography. The information they carry is secure because any attempt to intercept and measure one photon destroys the entanglement, revealing the eavesdropping. What is truly mind-bending is that entanglement persists even when photons are separated by vast distances. You can create entangled photons in a laboratory, send one to the moon and keep one on Earth, and the correlation remains. Measuring the Earth photon instantly affects the state of the moon photon, even though the distance between them prevents any signal traveling at or below the speed of light from explaining the correlation. The information about their shared quantum state somehow transcends space in a way that challenges our understanding of locality. This raises profound questions about the nature of memory and information. If entangled photons can maintain correlations across cosmic distances without any continuous physical connection, what does this tell us about how information is stored in the universe? Is information a property of individual particles, or is it a property of the relationships between particles? Does information exist in space, or does it exist in some more abstract realm that space merely represents? Current physics does not have complete answers to these questions. Quantum mechanics gives us mathematical tools to predict the behavior of entangled systems with extraordinary precision, but it does not provide a satisfying explanation of how entanglement works or what it means. We know that entangled photons preserve information about their shared origin, that this information survives separation and persists until measurement, and that the information cannot be used to send signals faster than light despite the instantaneous nature of the correlation. Some physicists believe entanglement reveals that the universe is fundamentally non-local, that separation in space is less fundamental than we thought, that reality at the quantum level is deeply interconnected in ways that only become apparent when we study correlations. Others interpret entanglement as evidence that information is more fundamental than matter or energy, that the universe is essentially an information processing system where particles are simply the physical manifestation of information states. Regardless of interpretation, entanglement demonstrates that light's memory extends beyond what individual photons carry. Information can be encoded in the quantum correlations between photons, in patterns that span space and persist over time in ways that transcend our classical understanding of memory. This quantum memory is fragile, easily destroyed by decoherence when the photons interact with their environment. But in the clean conditions of space, in carefully controlled laboratory experiments, quantum memory can be maintained, creating communication channels and computing substrates that have no classical equivalent. Light, it turns out, remembers not just in the information each photon carries individually, but in the information that emerges from quantum relationships between photons. This is memory at its most fundamental level, woven into the fabric of reality itself, existing in the abstract space of quantum states rather than in any physical location. It is memory that transcends space and time, memory that challenges our deepest assumptions about the nature of information and reality. Let us make this concrete. Let us follow the journey of a single photon from creation to observation, tracing the memory it accumulates along the way. We begin deep in the core of the Sun, where temperatures exceed 15 million degrees and nuclear fusion transforms hydrogen into helium, releasing enormous amounts of energy. In this process, gamma-ray photons are created, each carrying energy corresponding to a wavelength of about 1 picometer, far smaller than an atom. This photon immediately collides with nearby particles in the dense solar plasma. It is absorbed by an electron, then quickly re-emitted, but now in a slightly different direction and with slightly less energy. The photon scatters again and again and again. The core of the Sun is so dense that photons can travel only a tiny fraction of a millimeter before being absorbed and re-emitted. Each scattering event randomizes the photon's direction and slightly reduces its energy. This random walk through the Sun takes an extraordinarily long time. The photon we are following will take more than 100,000 years to work its way from the core to the surface, despite being created at the center of a sphere only 700,000 kilometers in radius. If it could travel in a straight line at the speed of light, the journey would take about 2 seconds. But the constant scattering forces the photon to take a path millions of times longer than a direct route. As the photon approaches the surface, the solar material becomes less dense. Scattering events become less frequent. The photon's energy has been reduced from gamma-ray to X-ray to ultraviolet and finally to visible light. By the time it reaches the photosphere, the visible surface of the Sun, the photon has a wavelength around 500 nanometers, appearing yellow-green to human eyes. All the information about its origin as a gamma-ray has been erased by countless interactions. The photon now carries memory only of the temperature and composition of the Sun's surface layers. Then, finally, the photon escapes into space. It travels outward at exactly the speed of light, unimpeded by the near-perfect vacuum. From Earth's perspective, this journey takes 8 minutes and 20 seconds. But from the photon's perspective, no time passes at all. The moment of leaving the sun's surface and the moment of arriving at Earth are the same moment in the photon's reference frame. The photon crosses the vast emptiness of space, traveling 93 million miles without a single interaction. It carries within its quantum state information about the sun's surface temperature, about the magnetic fields that shaped the region it came from, about the motion of the solar plasma that emitted it. This information is encoded in the photon's wavelength, its polarization, and the phase relationships it maintains with other photons emitted from the same region. As the photon approaches Earth, it enters our planet's magnetosphere, then the upper atmosphere. The atmosphere affects the photon's journey. Blue light scatters more than red light, which is why the sky appears blue during the day and red at sunrise and sunset. Our photon, being yellow-green, scatters moderately. It might bounce off a few air molecules, changing direction slightly but preserving most of its information. Finally, the photon enters your eye. It passes through the cornea and lens, which focus it onto your retina. There, it strikes a molecule of rhodopsin in a rod cell. The photon is absorbed, its energy causing the rhodopsin molecule to change shape. This shape change triggers a cascade of chemical reactions that ultimately generate an electrical signal in the optic nerve. The photon has been destroyed, its energy converted into chemical and electrical energy in your nervous system. But its memory has been transferred. The information it carried about the sun's surface has been encoded in neural activity in your brain. This entire journey, from nuclear fusion in the solar core to neural signal in your brain, has taken over 100,000 years from the photon's birth to its absorption. Yet the photon only existed as an independent entity for the last 8 minutes and 20 seconds. The rest of the time, its energy was passed from particle to particle through countless absorption and emission events. And from the photon's own perspective, even those 8 minutes took zero time. The journey that spanned a century of stellar processing and 93 million miles of space occupied no duration at all in the photon's reference frame. What does this tell us about memory? It tells us that memory can exist in multiple forms. The information about solar core conditions is carried by energy, passed from particle to particle for 100,000 years. The information about surface conditions is carried by a photon for 8 minutes of our time, zero time of its time. And finally, the information becomes neural memory, encoded in the pattern of neural connections in your brain. Each form of memory has different characteristics, different stability, different accessibility. But the chain of causality connects them all, creating an unbroken link from fusion in the solar core to conscious perception in a human mind. Now let us extend this story across far greater distances and times. Consider a photon emitted not from our nearby sun, but from a distant star hundreds or thousands of light years away. These photons carry memories far older than human civilization, information about cosmic events that occurred before our species existed, before our solar system formed, before even the Earth coalesced from the primordial nebula. Betelgeuse, the red supergiant star marking Orion's shoulder, lies approximately 640 light-years from Earth. When you look at Betelgeuse tonight, the photons entering your eye left that star in the year 1385 AD, during the Ming Dynasty in China, before the European Renaissance, before the Americas were known to European explorers. Those photons have been traveling through space for more than 6 centuries, carrying information about Betelgeuse's surface temperature, chemical composition, and brightness as it was in the 14th century. But Betelgeuse is relatively nearby. Consider more distant stars. Deneb, the bright star in Cygnus, lies about 2,400 light-years away. Light from Deneb that reaches us tonight left that star around 400 BC, during the golden age of Greek philosophy, when Socrates was teaching in Athens and the Parthenon was newly built. That light has been traveling through space for all of recorded human history, carrying unchanged information about a star's condition from an era when humans had no conception of what stars actually were. And these are still just nearby stars within our own galaxy. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light-years away. When you observe Andromeda, you are seeing light that left that galaxy before modern humans evolved, before the genus Homo emerged, during the Pliocene epoch when our distant ancestors were still primitive apes. That light has carried its memory across the void between galaxies for longer than our species has existed. What information do these ancient photons preserve? They tell us about stellar temperatures, which we infer from the spectrum of light, the distribution of energy across different wavelengths. They tell us about chemical composition through absorption lines, dark gaps in the spectrum where specific elements absorb specific wavelengths. They tell us about motion through Doppler shifts, subtle changes in wavelength caused by the star moving toward or away from us. They tell us about magnetic fields through Zeeman splitting and polarization patterns. Each of these pieces of information is encoded with remarkable precision. Spectroscopy can identify elements present in a star's atmosphere at concentrations of parts per million. Doppler measurements can detect velocity changes as small as a few meters per second. Photometry can measure brightness variations of less than 1%. All this information has been carried by photons across distances so vast that human minds struggle to comprehend them, preserved perfectly in the quantum states of massless particles. But there is something poignant about this memory. The information is always historical. When we observe a distant star, we are not seeing it as it is now. We are seeing it as it was when the light left hundreds or thousands or millions of years ago. For very distant objects, we are seeing them as they were in the ancient past, and we have no way to know their current state. They might have changed drastically. They might have exploded, collapsed into black holes, been consumed by larger stars. We cannot know until sufficient time has passed for light from those events to reach us. This means our view of the universe is fundamentally a view of history. We do not see the cosmos as it is, but as it was, with different parts seen at different historical epochs depending on their distance. The universe appears to us as a vast temporal collage, with nearby objects showing recent conditions and distant objects showing ancient conditions. Light's memory gives us access to cosmic history, but it denies us knowledge of the present state of anything beyond our immediate neighborhood. Yet there is profound value in this historical record. The light reaching us from distant galaxies shows us what the universe was like billions of years ago. We can observe galaxy formation in progress, star birth in ancient epochs, the universe when it was younger and different from today. By observing objects at different distances, we are essentially conducting cosmic archaeology, reconstructing the history of the universe from the memories carried by light across billions of years. And this record is complete in principle. Every photon that has ever been emitted by every object in the observable universe is still traveling somewhere, still carrying its memory. If we had instruments sensitive enough, if we could collect photons from every direction and every wavelength, we could in principle reconstruct the entire history of the observable universe from the information carried by light. The memory exists, written in photons scattered across the cosmos, waiting to be read by observers with sufficient knowledge and technology. The oldest memory accessible to us is carried by photons from the cosmic microwave background, the faint glow of radiation that fills all of space, arriving from every direction with nearly uniform intensity. These photons were emitted when the universe was just 380,000 years old, when space cooled enough for neutral atoms to form and light to travel freely for the first time. They have been traveling for 13.8 billion years, stretched from visible and infrared light into microwaves by the expansion of space, but still carrying information about the infant universe. What makes the cosmic microwave background extraordinary is its uniformity. The temperature is the same in all directions to better than 1 part in 100,000. This tells us something profound. The early universe was remarkably smooth, with density varying by only tiny amounts from one region to another. But those tiny variations are crucial. They represent the seeds that would later grow through gravitational attraction into galaxies, stars, planets, and eventually life. The photons of the cosmic microwave background preserve this information with exquisite detail. By mapping the temperature variations across the sky with high precision, we can reconstruct the pattern of density fluctuations in the early universe. We can determine the curvature of space, the density of matter and energy, the rate of expansion. We can test theories of cosmology and inflation. We can peer back to an epoch just a few 100,000 years after the Big Bang and see conditions that shaped everything that would follow. These photons are the oldest things we can directly observe. They are older than any star, any galaxy, any structure in the universe. They have been traveling for 99.9% of cosmic history, carrying their memory across distances that began when the observable universe was less than 1,000th its current size. And the information they carry has not degraded. It has simply been stretched, redshifted to longer wavelengths, but preserved with perfect fidelity. There is something almost sacred about these ancient photons. They are cosmic witnesses, the only things that remember what the universe was like before structure formed, before stars ignited, before complexity emerged. They have traveled farther and longer than any matter, any particle, any object in existence. They are pure memory, given form as electromagnetic radiation, carrying knowledge across the entire age of the universe. When astronomers study the cosmic microwave background, they are not merely measuring radiation. They are reading the universe's oldest memory, decoding information that has been preserved since before stars existed. It is like finding a perfect photograph from the universe's infancy, a snapshot so ancient that it predates everything familiar, everything we call structure or form. And the photograph is not stored in matter that could decay or be destroyed. It is stored in light itself, in photons that have been traveling since time began, carrying their eternal memory across the expanding cosmos. Before we speak of extinct stars, let us consider light we intentionally created to carry memory. In 1977, humanity launched two spacecraft, Voyager 1 and Voyager 2, on trajectories that would eventually take them beyond the solar system into interstellar space. Each carried a golden record, a phonograph disc containing sounds and images from Earth, intended as a message to any extraterrestrial intelligence that might someday encounter the spacecraft. But there is another message carried by the Voyagers, one written in light. As the spacecraft travel outward, they continue to communicate with Earth using radio waves, photons at wavelengths of several centimeters. These photons carry telemetry data, scientific measurements, status reports. They are artificial memories, deliberately encoded by human technology rather than naturally arising from physical processes. The photons from Voyager 1 now take more than 22 hours to reach Earth. The spacecraft is over 14 billion miles away, far beyond the orbit of Pluto, in the region where the solar wind from our sun meets the interstellar medium. Every signal we receive is memory from nearly a day in the past. We cannot communicate in real time. We send commands and wait almost 2 days for confirmation that they were received and executed. The photons bridge this vast distance, carrying our intentions outward and the spacecraft's responses inward. What makes this poignant is the weakness of the signal. Voyager transmits with just 23 watts of power, less than a refrigerator light bulb. By the time these photons cross 14 billion miles of space, they are spread so thin that Earth receives less than 1/10,000,000th of a watt. We detect individual photons, counting them one by one, extracting bits of information from the sparse arrival of particles that left the spacecraft almost a day ago. Yet the information persists. The photons remember what Voyager encoded in them. They travel through the near vacuum of interstellar space without scattering or absorption, maintaining their wavelength, their polarization, their timing. When they finally reach Earth's antennas, 70-meter dishes that focus their vast collecting area on a single point, the information can be decoded. We learn what Voyager measured a day ago, what its instruments detected, what status its systems report. This human-made memory system mirrors the natural one. Stars emit photons that carry information about stellar conditions. Voyager emits photons that carry information about spacecraft conditions. Both use the same physical principles, the same quantum mechanics, the same electromagnetic propagation through space. The difference is only in the intentionality, in the fact that Voyager's photons were designed to carry meaning while stars' photons simply carry whatever information physical processes happen to encode. In some distant future, perhaps millions of years from now, Voyager will pass near another star system. If intelligent beings exist there, if they possess technology to detect and analyze the spacecraft, they might intercept the radio emissions Voyager continues to transmit. Those photons, carrying information encoded in the 1970s, will have traveled for millions of years, preserving their message across distances and times that dwarf human civilization's entire existence. The photons will not know they carry a message. They will not understand the binary codes modulating their waves, the engineering data and scientific measurements formatted according to protocols designed by human engineers decades ago. They will simply propagate, preserving correlations between their electromagnetic field patterns and the states of Voyager's transmitter at the moment of emission. But if someone knows how to read the code, the message will be there, perfect and complete, waiting across the void. This is light's ultimate generosity. It carries natural information with the same fidelity as artificial information. It preserves astrophysical data with the same care as engineering telemetry. It makes no distinction between messages and noise, between meaningful and meaningless, between intentional and accidental. Light simply remembers, preserves, transmits, allowing consciousness at the receiving end to decide what matters and what does not. Now let us explore another kind of cosmic message, one that reveals how light can preserve memory of phenomena we cannot observe directly. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse, and if Earth happens to lie in the path of the beam, we detect regular pulses of radio waves with extraordinary precision. The most stable pulsars keep time more accurately than atomic clocks, varying by less than a microsecond over decades. This stability makes pulsars natural cosmic clocks, and the light they emit carries memory not just of the pulsar itself, but of everything the light encountered on its journey to Earth. When gravitational waves pass through space, they stretch and compress spacetime itself in a rhythmic pattern. This stretching affects the travel time of light, including the radio pulses from pulsars. By monitoring many pulsars simultaneously and looking for correlated timing variations, scientists can detect gravitational waves with wavelengths spanning light years. This technique, called pulsar timing arrays, has successfully detected gravitational waves from supermassive black hole binaries at the centers of distant galaxies. These waves have frequencies of nanohertz, oscillating once every few years. They are far too slow to be detected by instruments like LIGO, which observe much higher frequency gravitational waves from merging stellar mass black holes and neutron stars. Pulsar timing arrays fill a different observational window, revealing gravitational phenomena at cosmic scales. The photons arriving from pulsars carry this information in their timing. Each photon arrives slightly early or slightly late depending on how spacetime was curved along its path. The photons do not know about gravitational waves. They simply follow geodesics, the straightest possible paths through curved spacetime. But by accumulating many photons over years and analyzing subtle patterns in their arrival times, we can reconstruct the gravitational wave background that permeates the universe. This is memory at a profound level. The photons preserve information about the geometry of spacetime itself, about massive objects whose gravity warped the path of light, about dynamical processes that created ripples in the fabric of reality. The information is not encoded in the photon's internal state like wavelength or polarization. It is encoded in when the photon arrives, in the timing relationship between photons from different pulsars, in patterns that only emerge when comparing data from multiple sources. Gravitational lensing provides another example of light carrying memory of spacetime geometry. When light passes near a massive object, the object's gravity bends the light's path. This creates multiple images of distant sources, magnifies their apparent brightness, and distorts their shapes. By studying these distortions, we can map the distribution of matter along the line of sight, including dark matter that emits no light itself, but whose gravity affects photons passing nearby. The photons carry this information passively. They do not interact with dark matter directly, experiencing only the curvature of spacetime that dark matter's gravity creates. But that curvature leaves its signature in the path the photon follows, in the direction from which it arrives, in the time it takes to complete its journey. Multiple photons from the same source arriving from slightly different directions tell us that spacetime between us and the source is curved in specific ways, and from this we can infer the mass distribution responsible for the curvature. Every photon that has traveled through the universe carries a complete record of the spacetime geometry it encountered. This information exists in the photon's world line, the four-dimensional path through space and time that the photon followed from emission to absorption. Different photons from the same source follow different world lines if they leave at different times or from different locations, and comparing these world lines reveals the structure of spacetime between source and observer. We are only beginning to learn how to read this information. Current techniques extract crude features, overall mass distributions, large-scale curvature. But in principle, a sufficiently detailed measurement of photons from many sources could reconstruct the complete geometry of spacetime in enormous detail. Every gravitational field, every massive object, every dynamical process that creates spacetime curvature leaves its signature in the paths that photons follow. Light's memory extends beyond electromagnetic information to include gravitational information, making photons carriers of the deepest structure of reality itself. But not all light's memories are ancient in the sense of being created long ago. Some of light's most poignant memories come from relatively recent events involving stars that have already ceased to exist. Consider this. Many of the bright stars visible in Earth's night sky are massive, short-lived objects that burn through their nuclear fuel in mere millions of years. Some of them have already died, already exploded as supernovae, already collapsed into neutron stars or black holes. But we do not know this yet because the light from those death events has not reached us. When we look at these stars tonight, we see them shining steadily as they did decades or centuries ago when the light we observed departed. The stars appear alive, normal, eternal. But some of them are already dead. The light carrying memory of their deaths is rushing toward us at the speed of light. And when it arrives, we will witness the star's destruction in real time as far as we can tell, even though the actual event occurred years or centuries ago. This creates a strange temporal situation. The star exists in our observations, preserved in the memory of light that left before the star died. But the star no longer exists in reality. We are seeing a ghost, an afterimage, a memory of something that has ceased to be. And we will continue to see this ghost for as long as light from before the death continues to arrive. Only when light from after the death reaches us will we finally see the truth. Betelgeuse is a prime example of this situation. This red supergiant is nearing the end of its life. It could explode as a supernova at any time, perhaps tomorrow, perhaps 100,000 years from now. But it might have already exploded. The light from such an explosion would take 640 years to reach us. Betelgeuse could have gone supernova in the year 1400 AD, and we would not know until the light from that event arrives around 2040 AD. From our perspective, Betelgeuse shines normally in the constellation Orion, but in reality, it might already be a rapidly expanding cloud of debris with a neutron star or black hole at its core. This is not mere speculation. It is certain that some stars we see tonight are already dead. The universe is too large, light too slow, and stellar lifetimes too short for it to be otherwise. We are surrounded by ghosts, by memories of stars that no longer exist, preserved in photons that continue their journey toward us, carrying information about objects that ceased to exist centuries or millennia ago. When the light from a star's death finally reaches us, when we see the supernova explosion light up the sky, we will be witnessing an event that happened in the distant past. We will see the star brighten over days or weeks, watch it fade over months and years, observe the expanding shell of debris, all in real time as far as our perception is concerned. But we will be watching history, not the present. The actual explosion happened centuries ago, perhaps before any human currently alive was born. Light thus creates a universe of memories where the present is unknowable except for our immediate vicinity. Everything we see is past, frozen in the photons that carry information from then to now, from there to here. The cosmos we observe is not the cosmos that exists. It is a collection of memories, of historical snapshots, of light's perfect but delayed recollections of events scattered across time and space. This has profound implications for our understanding of reality. We speak of the universe as if it were a single, unified entity that exists simultaneously everywhere. But this is an illusion created by our limited perspective on Earth. There is no universal now that extends across cosmic distances. Every observation is of the past. Every photon carries old news. The universe exists as a four-dimensional structure where time and space are intimately connected, where the present at one location is the distant past at another, where simultaneity is relative and observer-dependent. Light's memory reveals this truth. Photons do not experience time, but they connect events across time, creating causal links between emission and absorption, between past and present. The universe remembers itself through light, through photons that carry information from every event to every potential observer, creating a web of memories that defines the structure of cosmic history. We arrive now at a question that pushes into philosophy and the foundations of quantum mechanics. Consider a photon traveling through empty space between galaxies, emitted by a star billions of years ago, traveling for eons without encountering a single particle of matter. This photon carries information about its source, encoded in its wavelength, polarization, direction, and phase. But if nothing ever observes this information, if the photon never reaches a planet with instruments to detect it, if it simply travels forever through expanding space until the universe grows cold and dark, does the information still exist? From a classical perspective, the question seems almost silly. Of course, the information exists. The photon has definite properties: wavelength, energy, momentum. These properties encode information about the source. The fact that nothing reads this information does not mean it is not there, any more than an unread book contains no information simply because no one is currently reading it. But quantum mechanics complicates this picture. In quantum theory, properties like position and momentum do not have definite values until they are measured. Before measurement, the photon exists in a superposition of multiple possible states. The wave function describes probabilities for different outcomes if a measurement were to occur, but until that measurement happens, the photon does not have a definite value for most of its properties. So what does it mean for an unobserved photon to carry information? If the information only becomes definite when measurement collapses the wave function, does the information exist in any meaningful sense before that moment? Or is information something that only comes into being through observation, through the interaction that collapses quantum superposition into classical reality? This is one of the deepest questions in quantum mechanics, related to the measurement problem and the nature of wave function collapse. Different interpretations of quantum mechanics give different answers. In the Copenhagen interpretation, observation is fundamental. The wave function represents our knowledge about the system, and measurement updates that knowledge, collapsing superposition into definite states. Information, in this view, is created by observation. Unobserved photons carry potential information, but not actual information. In the many worlds interpretation, there is no collapse. The wave function never changes except through deterministic evolution according to Schrödinger's equation. Measurement simply correlates the observer's state with the measured system's state, branching reality into multiple worlds where different outcomes occur. Information exists in all branches, encoded in the complete wave function of the universe. Observation does not create information. It merely determines which branch of reality the observer finds themselves in. In objective collapse theories, wave function collapse is a real physical process that occurs spontaneously under certain conditions, independent of observation. Information would exist in definite form whenever collapse occurs, even without conscious observers. Unobserved photons would carry real information, encoded in their collapsed quantum states. The choice between these interpretations remains unresolved. Experiments cannot distinguish them because they all make identical predictions for observable outcomes. But the question has profound implications for understanding what light's memory means. Is information an objective property of the universe that exists independent of observation? Or is information something that emerges through the act of observation, meaningless without an observer to decode it? Perhaps the answer lies in recognizing that information is relational rather than absolute. A photon carries information about its source relative to a potential observer. The information exists as a correlation between the photon state and the source's state at the moment of emission. This correlation is objective and observer-independent. But accessing the information requires interaction, measurement, observation. The information is there, but it only becomes manifest, only becomes known, only enters the realm of classical reality when an observation occurs. In this view, light's memory is real but latent. Photons genuinely carry information across space and time, encoding properties of their sources in their quantum states. But this information exists in a quantum limbo, neither fully real nor entirely unreal, until observation brings it into definite existence. Memory, in this sense, is potential rather than actual, waiting to be actualized through interaction. This philosophical subtlety does not diminish light's importance as a memory medium. Whether we say the information exists in unobserved photons or merely that it potentially exists, the practical consequence is the same. Photons preserve correlations between distant events, creating the possibility for information transfer across space and time. This preservation is reliable, deterministic, and predictable. We can calculate with precision what information a photon will reveal when observed, even if we cannot say with certainty that the information existed before observation. This brings us to an even more speculative question. Does consciousness play any special role in light's memory? Quantum mechanics suggests that observation is necessary to collapse wave functions and actualize information. But what counts as observation? Does it require consciousness? Or is any physical interaction sufficient? The question has been debated since the early days of quantum mechanics. Some physicists, influenced by results like the delayed choice experiment and the quantum eraser, have argued that conscious observation is fundamental to quantum mechanics. In this view, information only becomes real when a conscious mind observes it. Unobserved events exist in superposition, and consciousness collapses the wave function, selecting which branch of reality becomes actual. If this were true, it would have extraordinary implications for light's memory. Photons would carry potential information, but that information would not become real until a conscious being observed it. The universe's history, encoded in light traveling through space, would not be definite until consciousness looked back and observed it. The past would be created by present observation, a retroactive determination of what happened based on what we choose to measure now. This seems to violate causality and common sense. How can present observation determine past events? But quantum mechanics already includes phenomena that challenge our intuitions about time and causality. The delayed choice experiment shows that decisions made in the present can affect the behavior of photons in ways that seem to reach back into the past. The quantum eraser shows that information can be erased retroactively, making it impossible to determine which path a photon took even after it has completed its journey. Most physicists reject the idea that consciousness is fundamental to quantum mechanics. They argue that observation is simply any interaction that causes decoherence, the loss of quantum coherence due to entanglement with the environment. Consciousness is not required. A photomultiplier tube, a photographic plate, even a dust grain floating in space can serve as an observer in the quantum mechanical sense. Observation is physical interaction, not mental awareness. In this view, light's memory is independent of consciousness. Photons preserve information through their quantum states, and this information becomes definite through physical interactions, whether or not those interactions involve conscious beings. The role of consciousness is merely to interpret the information, to extract meaning from physical measurements, not to create the information through observation. Yet there remains something mysterious about the connection between light and consciousness. Every bit of information we have about the external universe comes to us through light or other electromagnetic radiation. Vision, our primary sense, operates by detecting photons. Our knowledge of cosmic history, of distant stars and ancient events, is entirely derived from light's memory. Consciousness and light are intimately connected, not because consciousness creates light's memory, but because light is the medium through which consciousness accesses information about reality beyond the immediate physical body. Perhaps the relationship is best understood as reciprocal. Light preserves information about physical events, creating memories that persist across space and time. Consciousness reads these memories, extracting meaning and building mental models of reality. Neither is fundamental in an absolute sense. Information exists in the correlations between physical states. Light carries these correlations with unparalleled efficiency. Consciousness decodes the correlations and constructs understanding. Each plays a role in the larger process of turning raw physical events into remembered, understood, meaningful experience. Comparing light's memory to other forms of memory reveals both its extraordinary strengths and its inherent limitations. Human memory, stored in neural connections and molecular configurations, is highly unreliable. We forget, we misremember, we unconsciously alter memories each time we recall them. Yet human memory has something that light's memory lacks. It has meaning. Human memory preserves not just facts, but the emotional context, the subjective experience, the significance of events. Light remembers physics perfectly but knows nothing of meaning. A photon can carry precise information about a star's temperature, but it cannot tell you why that star matters, what it means to anyone, whether its light illuminates worlds where beings look up in wonder or falls unnoticed on barren rocks. The information is objective, quantitative, devoid of interpretation or significance. Computer memory occupies a middle ground. Digital storage is more reliable than human memory but less perfect than light's memory. Bits can flip due to cosmic rays or thermal noise. Magnetic domains can degrade. Storage media can fail. But computer memory has structure and organization. It preserves not just data, but the relationships between data, the categories and hierarchies and connections that give information meaning and utility. Light's memory is pure and simple. It preserves correlations between physical states. The photon's wavelength correlates with the source's temperature. Its direction correlates with the source's location. Its polarization correlates with magnetic field orientation. These correlations are preserved with perfect fidelity as long as the photon travels through empty space without interaction. But there is no organization, no hierarchy, no context. The information exists as raw physical properties without interpretation. This means light alone cannot create knowledge. Information must be extracted, organized, interpreted by something capable of understanding. Human consciousness performs this role when we observe stars and construct theories about their nature. Scientific instruments perform this role when they sort photons by wavelength or polarization and record statistical patterns. The knowledge is not in the light itself, but in what we make of the light, how we decode its memory and integrate that memory into our understanding of reality. Yet light's simplicity is also its strength. Human memory is vulnerable to bias, wishful thinking, emotional distortion. Computer memory can be hacked, corrupted, deliberately falsified. But light's memory cannot lie. It preserves correlations determined by physical law, unaffected by desires or intentions. If you know how to read light correctly, if you understand the physics well enough, light will tell you the truth about physical reality with absolute reliability. This makes light's memory foundational to science. All of empirical observation ultimately traces back to detecting light or other electromagnetic radiation. Every measurement, every experiment, every astronomical observation relies on light to carry information from the observed system to our instruments. Science trusts light to be honest, to preserve information accurately, to maintain correlations between distant events. And light has never betrayed that trust. Every time we have understood the physics well enough to interpret light's memory correctly, that memory has proven accurate. Taking a step back, we can see light's memory as part of a larger pattern. The universe itself is a memory system. Information about past events is preserved in the current state of physical systems. The arrangement of stars remembers the gravitational collapse of gas clouds billions of years ago. The composition of Earth's crust remembers the geological processes that shaped our planet. The genetic code of living organisms remembers evolutionary history stretching back billions of years. In this sense, everything is memory. The present state of any system contains information about its past. Physical laws ensure that information is conserved, that the evolution of systems follows deterministic rules that preserve correlations between past and present. Entropy increases, and this increase is irreversible, creating an arrow of time that distinguishes past from future. But information is not destroyed by entropy. It merely becomes more diffused, more difficult to access, spread across more degrees of freedom. Light's memory fits into this larger picture as perhaps the purest form of information preservation. While most physical systems accumulate entropy, losing accessible information as they evolve. Photons traveling through empty space experience no entropy increase at all. Their quantum states evolve deterministically and reversibly. The information they carry is not degraded or hidden in microscopic degrees of freedom. It remains accessible, encoded in measurable properties like wavelength and polarization. This makes light a kind of privileged medium for cosmic memory. Other physical systems remember through their current state, but that state is constantly changing, constantly evolving away from the past, constantly accumulating new entropy that buries old information deeper and deeper in complexity. Light, by contrast, preserves information in a form that does not age, does not evolve, does not accumulate entropy. The photon state when it is absorbed is fundamentally the same as its state when it was emitted, just shifted to longer wavelengths by cosmological expansion but otherwise unchanged. If we imagine the universe as a vast information processing system, light serves as the communication network. It carries messages from one part of the system to another, from past to present, from distant locations to local receivers. These messages are encoded in the simplest possible way, as properties of individual photons or correlations between multiple photons. The encoding is robust, resistant to noise and interference, capable of traversing cosmic distances without degradation. Perhaps this is not accidental. Perhaps light's unique properties as a memory medium are connected to its role as the universal speed limit, the maximum rate of causality. If information is fundamental to physics, if the universe is essentially an information structure, then light might be the natural carrier of that information, the means by which different parts of the information structure remain connected and correlated across space and time. This is speculative, but it points toward a deeper understanding. Light is not just electromagnetic radiation that happens to carry information. Light is the physical manifestation of information propagating through spacetime at the maximum possible speed. A photon is information given physical form, allowed to travel, to connect events, to create correlations that define the causal structure of reality. When we receive light from distant stars, when we detect photons from the cosmic microwave background, when we observe interference patterns in a laboratory, we are not simply measuring particles or waves. We are reading the information structure of the universe, decoding the messages that connect distant events, accessing memories that define cosmic history. Light is how the universe remembers itself, and we, through our observations, participate in that remembering. Astronomy as memory reading. Everything we know about the universe beyond our immediate vicinity comes from reading light's memory. Astronomy is fundamentally the practice of collecting photons from distant sources and decoding the information they carry. Every telescope, every spectrograph, every camera attached to astronomical instruments is a device for extracting memory from light. The process begins with collection. Telescopes are essentially light buckets, devices with large collecting areas that gather photons from specific directions in the sky. The larger the telescope, the more photons it can collect, and the fainter the objects it can observe. This matters because distant objects are faint, not because they are intrinsically dim, but because their light has spread across an enormous sphere by the time it reaches us. Consider a star 10,000 light-years away. Its light has traveled for 10,000 years, spreading outward in an expanding sphere. By the time the light reaches Earth, it has spread across a sphere with a surface area of about 10,000 trillion square meters. Earth's entire cross-section intercepts only about 1/10 billionth of 1/trillionth of the total light. We receive an extraordinarily tiny fraction of the photons the star emitted, and each photon we do receive becomes precious, carrying irreplaceable information about that distant object. Once collected, light must be analyzed. Spectroscopy spreads light into its component wavelengths, creating a spectrum that reveals absorption and emission lines corresponding to specific elements and molecules. By studying which wavelengths are present or absent, we can determine chemical composition, temperature, density, and motion of the emitting or absorbing material. The spectrum is essentially a detailed decoding of the information carried by photons of different energies. Photometry measures the brightness of objects, tracking how their light output changes over time. Variable stars brighten and dim in regular patterns. Eclipsing binary systems show periodic drops in brightness when one star passes in front of the other. Even planets can be detected by the tiny dimming they cause when they transit in front of their host stars. Each brightness variation is a message carried by light, information about processes occurring at the source. Polarimetry analyzes the polarization state of light, revealing information about magnetic fields, scattering processes, and the geometry of emission regions. Light from stars is usually unpolarized, but light scattered by dust or passing through magnetic fields becomes polarized. By measuring polarization, we can map magnetic field structures in space, detect dusty disks around young stars, and identify regions where scattering has occurred. Interferometry combines light from multiple telescopes, creating interference patterns that contain information about the source's structure at angular scales far smaller than any single telescope could resolve. This technique has allowed astronomers to image the surfaces of stars other than our Sun, to resolve binary star systems separated by tiny angles, even to capture the shadow of the supermassive black hole at our galaxy's center. The information was always there, encoded in the phase relationships between photons arriving from slightly different directions, waiting for instruments sophisticated enough to decode it. All these techniques are ways of reading light's memory. The photons carry information encoded in multiple dimensions: wavelength, intensity, polarization, phase, direction, time of arrival. Each measurement extracts part of this information, revealing something about the source that emitted the light. By combining multiple types of measurements, by collecting photons across many wavelengths and analyzing their properties in detail, astronomers reconstruct the physical conditions at sources light-years or billions of light-years away. The reliability of this process is remarkable. We have never visited other stars, never sent probes to distant galaxies, never directly sampled the material of cosmic objects beyond our solar system. Yet we know the composition of stars, the temperature of nebulae, the mass of black holes, the expansion rate of the universe. All this knowledge comes from reading light's memory, from trusting that photons preserve information accurately across cosmic distances, from understanding the physics well enough to decode the messages correctly. Light's memory has practical applications beyond astronomy. Quantum communication and quantum cryptography exploit the properties of photons to create communication channels that are fundamentally secure, protected not by computational complexity but by the laws of quantum mechanics themselves. The basic idea is simple. Information can be encoded in the quantum state of a photon, perhaps in its polarization or in correlations between entangled photon pairs. The sender transmits these photons to a receiver, who measures them and extracts the information. But here is the crucial point. Any attempt to intercept and measure the photons will disturb their quantum states in detectable ways. The eavesdropper cannot read the information without revealing their presence. This security comes from the quantum no-cloning theorem, which states that it is impossible to create an exact copy of an unknown quantum state. An eavesdropper trying to intercept photons cannot copy them without disturbing the original. They must measure the photons to learn anything, but measurement collapses the wave function, changing the state. The legitimate receiver will notice the disturbance and know that the communication has been compromised. Quantum key distribution, or QKD, uses this principle to allow two parties to share a secret encryption key with absolute security. The sender transmits photons with randomly chosen polarizations. The receiver measures them using randomly chosen measurement bases. After the transmission, they publicly compare which bases they used but not the results. Where their bases matched, they can be confident that their measurements gave identical results, providing shared random bits that can serve as an encryption key. Any eavesdropper would have introduced detectable errors, revealing their presence and allowing the parties to discard the compromised key and try again. This technology is already operational. Quantum communication networks exist in several countries, using fiber optic cables to transmit individual photons between secure facilities. Satellites equipped with quantum communication systems have been launched, creating the potential for global quantum-secured communication networks. The technology is moving from laboratory demonstrations to practical deployment, creating communication channels whose security is guaranteed by the fundamental properties of light's quantum memory. Entangled photons add another layer to quantum communication. When two photons are entangled, their quantum states are correlated in ways that cannot be explained by classical physics. Measuring one photon instantly affects the state of the other, regardless of the distance between them. This correlation can be used for quantum teleportation, a process where the quantum state of one photon is transferred to another photon at a distant location. Despite its science fiction name, quantum teleportation does not involve moving matter or energy faster than light. Instead, it uses entanglement and classical communication to reconstruct a quantum state at a new location while destroying it at the original location. The information about the quantum state is preserved, carried partially by entangled photons and partially by classical signals, allowing the state to be recreated perfectly without ever existing in between. These applications demonstrate that light's memory is not just a passive storage medium. It is an active resource that can be manipulated, controlled, and used to perform information processing tasks impossible with classical systems. The quantum properties that allow photons to preserve information perfectly also enable fundamentally new ways of encoding, transmitting, and securing that information. Another practical application of light's memory is holography, a technique for recording and reconstructing three-dimensional information about objects using interference patterns in light. Unlike photographs, which capture only the intensity of light at each point, holograms record both intensity and phase, preserving complete information about the light field reflected from an object. Creating a hologram involves splitting a laser beam into two paths. One path illuminates the object, and the reflected light is directed onto a recording medium. The other path goes directly to the recording medium as a reference beam. Where these two beams intersect, they create an interference pattern determined by the phase relationship between them. This pattern is recorded photographically or digitally. To reconstruct the image, the hologram is illuminated with light similar to the original reference beam. The recorded interference pattern diffracts this light, recreating the wavefronts that originally came from the object. The reconstructed light appears to be coming from where the object was, creating a three-dimensional image that can be viewed from different angles, with parallax and depth perception just like viewing the actual object. What makes holography remarkable is that it is a form of distributed memory. Every part of the hologram contains information about the entire object, just with different resolution. You can cut a hologram in half and each half still shows the complete three-dimensional image, just with reduced clarity. This is very different from a photograph, where cutting away part of the image loses that information completely. This distributed property arises because holography records phase relationships in light fields rather than just intensities. Phase encodes information about where light came from and how it traveled to reach the recording medium. By preserving phase across the entire hologram, the recorded pattern contains enough information to reconstruct the complete light field, allowing full three-dimensional visualization. Modern digital holography extends these principles using computer-generated holograms and computational reconstruction. Instead of physically recording interference patterns on film, we can calculate what pattern would be needed to produce a desired light field and display that pattern using spatial light modulators or other devices. This allows dynamic holographic displays that can change in real time, creating three-dimensional images without the need for special glasses or other viewing aids. The key insight is that complete information about a three-dimensional scene is encoded in the two-dimensional light field passing through any plane. If you can measure not just the intensity but also the phase and direction of light at every point in a plane, you have enough information to reconstruct the entire three-dimensional structure of everything visible from that plane. Light's memory, encoded in the phase relationships between photons, contains this three-dimensional information in a two-dimensional form. This principle extends beyond visible light. Holographic techniques work with any wavelength of electromagnetic radiation. Microwave holography creates images using radar signals. X-ray holography images objects at atomic scales. Acoustic holography uses sound waves to create three-dimensional images underwater or inside solid materials. In each case, the underlying principle is the same. Record phase information in a wave field, and you can reconstruct complete three-dimensional information about the sources and scatterers of those waves. Light's memory enables medical and scientific imaging techniques that have revolutionized our ability to see inside opaque objects without destroying them. Optical coherence tomography, or OCT, uses near-infrared light to image biological tissues with micrometer resolution, creating detailed three-dimensional maps of structures below the surface. The technique works by measuring the time delay of light reflected from different depths, using interferometry to detect echoes with extraordinary precision. OCT has become standard in ophthalmology, allowing doctors to image the retina, optic nerve, and other structures inside the eye. The images reveal details invisible to conventional examination, enabling early detection of diseases like glaucoma, macular degeneration, and diabetic retinopathy. The technique is non-invasive, requiring only that light be shined into the eye and the reflected photons be analyzed. The photons carry memory of their journey into the tissue and back, encoding information about structures they encountered along the way. Similar principles apply to other imaging modalities. Fluorescence microscopy uses light to excite molecules that then emit photons at different wavelengths. By capturing these emitted photons, scientists can visualize specific molecules within cells, tracking their location and movement with precision. The emitted photons carry memory of which molecules they came from, allowing identification and localization of specific proteins, nucleic acids, or other biological structures. Super-resolution microscopy pushes beyond the diffraction limit, achieving resolution far better than traditional optical microscopy should allow. Techniques like STORM, PALM, and STED use clever tricks with fluorescent molecules and precise timing to determine the position of individual molecules with nanometer accuracy. The photons emitted by these molecules carry information about their location encoded in the timing and intensity of emission. By analyzing thousands of photons from many molecules, scientists reconstruct images showing cellular structures at near-molecular resolution. All these techniques rely on light's ability to carry memory. Photons interact with matter, acquiring information about what they encountered, then travel to detectors where that information is decoded. The memory is encoded in wavelength, timing, intensity, polarization, or phase. Advanced instrumentation extracts this information with extraordinary sensitivity, creating images that reveal hidden structures and invisible processes. The future promises even more sophisticated applications. Quantum imaging uses entangled photons to image objects with reduced light levels or to see through turbulence and scattering. Ghost imaging reconstructs images of objects using photons that never actually touched the object, relying on quantum correlations with other photons that did interact. Computational imaging combines measurements from multiple sources or at multiple wavelengths, using algorithms to reconstruct detailed images from incomplete or distorted data. In each case, the fundamental principle remains the same. Light interacts with matter, acquires information, preserves that information during propagation, and delivers it to observers who can decode the memory. The sophistication lies in understanding how information is encoded, how it can be extracted, how multiple measurements can be combined to reveal more than any single measurement could show. Light provides the medium, quantum mechanics provides the rules, and human ingenuity provides the techniques for reading memory with ever greater precision. Light's memory enables medical and scientific imaging techniques that have revolutionized our ability to see inside opaque objects without destroying them. Optical coherence tomography, or OCT, uses near-infrared light to image biological tissues with micrometer resolution, creating detailed three-dimensional maps of structures below the surface. The technique works by measuring the time delay of light reflected from different depths, using interferometry to detect echoes with extraordinary precision. OCT has become standard in ophthalmology, allowing doctors to image the retina, optic nerve, and other structures inside the eye. The images reveal details invisible to conventional examination, enabling early detection of diseases like glaucoma, macular degeneration, and diabetic retinopathy. The technique is non-invasive, requiring only that light be shined into the eye and the reflected photons be analyzed. The photons carry memory of their journey into the tissue and back, encoding information about structures they encountered along the way. Similar principles apply to other imaging modalities. Fluorescence microscopy uses light to excite molecules that then emit photons at different wavelengths. By capturing these emitted photons, scientists can visualize specific molecules within cells, tracking their location and movement with precision. The emitted photons carry memory of which molecules they came from, allowing identification and localization of specific proteins, nucleic acids, or other biological structures. Super-resolution microscopy pushes beyond the diffraction limit, achieving resolution far better than traditional optical microscopy should allow. Techniques like STORM, PALM, and STED use clever tricks with fluorescent molecules and precise timing to determine the position of individual molecules with nanometer accuracy. The photons emitted by these molecules carry information about their location encoded in the timing and intensity of emission. By analyzing thousands of photons from many molecules, scientists reconstruct images showing cellular structures at near-molecular resolution. All these techniques rely on light's ability to carry memory. Photons interact with matter, acquiring information about what they encountered, then travel to detectors where that information is decoded. The memory is encoded in wavelength, timing, intensity, polarization, or phase. Advanced instrumentation extracts this information with extraordinary sensitivity, creating images that reveal hidden structures and invisible processes. One of the most remarkable applications of light's memory is LIGO, the Laser Interferometer Gravitational Wave Observatory. This instrument uses light to detect gravitational waves, ripples in spacetime caused by cataclysmic cosmic events like merging black holes. The detection principle is elegant. Split a laser beam and send the two parts down perpendicular arms several kilometers long. Bounce each beam off mirrors and recombine them. If spacetime is flat, the beams return in phase and interfere destructively, producing darkness. If a gravitational wave passes through, it stretches one arm while compressing the other, causing the beams to return slightly out of phase and creating a flash of light. The precision required is staggering. LIGO must detect changes in arm length smaller than 1/10,000th the diameter of a proton. This is equivalent to measuring the distance to the nearest star to within the width of a human hair. Yet LIGO achieves this precision using light's memory of phase relationships. The photons remember how far they traveled with precision limited only by quantum mechanics. And by accumulating many photons and analyzing their interference patterns, the system detects spacetime distortions too small to affect anything made of matter. When LIGO detected its first gravitational wave in 2015, the signal came from two black holes, each about 30 times the mass of the Sun, spiraling together and merging 1.3 billion years ago. The gravitational waves from this collision traveled through space for over 1 billion years, finally reaching Earth and causing LIGO's arms to change length by less than the width of an atomic nucleus for a fraction of a second. The light that detected this carried memory of the spacetime distortion. The photons traveled down LIGO's arms, bounced off mirrors, and returned to the beam splitter. Their travel time changed by femtoseconds, millionths of a billionth of a second, because the gravitational wave stretched and compressed space as they traveled. This timing change translated into phase shifts that created measurable interference patterns when the beams recombined. What makes this extraordinary is that light preserved information about a geometric distortion so small that it defies human intuition. The gravitational wave stretched space by 1 part in 10 to the 21st. If the arm were expanded to the size of the Milky Way galaxy, the stretch would be about the width of a human hair. Yet the photons faithfully preserved this information, encoding it in their quantum states, delivering it to detectors that could decode the memory and reveal the presence of gravitational waves. Since that first detection, LIGO and its partner observatory Virgo have detected dozens of gravitational wave events, ranging from merging black holes to colliding neutron stars. Each detection relies on light's perfect memory of phase, on the ability of photons to preserve timing information with quantum precision, on the interference patterns that reveal minute distortions in spacetime geometry. This application shows that light's memory extends beyond electromagnetic phenomena. Photons are sensitive to gravity, following curved paths through spacetime, experiencing time dilation in gravitational fields, preserving information about spacetime geometry in their world lines and timing. When we use light to detect gravitational waves, we are reading a memory that connects electromagnetic physics to gravitational physics, showing that photons carry information about the deepest structure of reality itself. While LIGO represents light's memory at the frontiers of fundamental physics, fiber optic communication represents its application to practical information technology. Every day, trillions of photons carry data through fiber optic cables spanning the globe, enabling the internet, telecommunications, and modern information infrastructure. These photons preserve digital information encoded in pulses of light, traveling through glass fibers at nearly the speed of light with minimal loss or distortion. Fiber optic cables work by total internal reflection. Light enters the fiber at one end and bounces off the walls repeatedly as it travels down the cable. The walls are designed so that light hitting them at shallow angles reflects completely rather than escaping, keeping the light trapped inside the fiber for distances of hundreds of kilometers. Different wavelengths of light can travel simultaneously through the same fiber, each carrying independent data streams in a technique called wavelength division multiplexing. The photons in fiber optic systems carry memory in their timing and wavelength. Data is encoded as pulses of light, with presence or absence of a pulse representing binary ones and zeros. The wavelength determines which data channel the photon belongs to, allowing multiple conversations to share the same physical cable. The timing determines when each bit was transmitted, allowing the receiver to reconstruct the data stream in the correct sequence. What makes fiber optics remarkable is the fidelity with which photons preserve this information. Modern fibers can transmit light for hundreds of kilometers with only about 3% signal loss. The photons maintain their wavelength, polarization, and timing with extraordinary precision. Dispersion, the tendency for different wavelengths to travel at slightly different speeds, is carefully controlled through fiber design. The result is that information encoded in light at one end of a transoceanic cable arrives essentially unchanged at the other end, thousands of kilometers away. The internet depends on this reliability. Every email, every web page, every video stream travels as photons through fiber optic networks. The photons are ephemeral, existing for only milliseconds or seconds before being absorbed and their information re-encoded in new photons by repeaters and routers. But during their brief existence, they carry memory with perfect fidelity, ensuring that information is not corrupted or lost during transmission. This reveals something important about light's memory. Duration is not necessary for reliability. A photon that exists for only milliseconds preserves information just as faithfully as one that travels for billions of years. What matters is not how long the photon exists, but that it maintains its quantum state throughout its journey. In fiber optics, photons are created, transmit data, and are destroyed in rapid succession, each carrying memory for a fleeting moment before passing that memory to its successor. The global fiber optic network is thus a vast memory system where information flows as light, preserved in quantum states of photons, transmitted at nearly the speed of causality, decoded and re-encoded millions of times per second. It is an artificial version of what stars and galaxies do naturally, using light to carry information across distances, preserving data in photon states, enabling communication that would be impossible without light's unique properties. Light's memory includes momentum, despite photons having no mass. This momentum is real and measurable, exerting pressure on anything that absorbs or reflects light. The pressure is tiny by everyday standards, but in space where there is no friction or air resistance, photon momentum can propel spacecraft using solar sails, large reflective surfaces that catch sunlight and convert photon momentum into thrust. The physics is straightforward. When a photon hits a surface, it transfers its momentum to that surface. If the photon is absorbed, the momentum transfer equals the photon's momentum. If the photon is reflected, the momentum transfer is twice the photon's momentum because the photon reverses direction, requiring a momentum change of twice its initial value. By accumulating billions of photons per second, a solar sail experiences continuous thrust that can accelerate it to high velocities over time. Several spacecraft have demonstrated solar sail propulsion. Icaros, launched by Japan in 2010, successfully used a solar sail to fly through the inner solar system. LightSail 2, launched in 2019, raised its orbit using only sunlight pressure, proving that solar sails can provide sustained propulsion for long-duration missions. Future missions might use enormous sails to reach the outer solar system or even nearby stars, accelerating to velocities impossible with chemical rockets. What makes this relevant to memory is that photon momentum carries information about the light source. The momentum points in the direction the light is traveling, preserving information about where it came from. The magnitude of the momentum depends on the photon's wavelength, carrying information about the source's temperature and emission spectrum. When a solar sail experiences thrust, it is reading this information, extracting momentum memory from photons and converting it into kinetic energy. Proposals for interstellar missions envision using powerful lasers on Earth or in orbit to push light sails to relativistic velocities. The laser photons would carry enormous momentum, and by reflecting these photons, a small spacecraft could accelerate to perhaps 20% the speed of light over a period of years. The photons from the laser would carry memory of their terrestrial origin, and that memory would be transferred to the spacecraft as momentum, enabling a machine built by humans to reach another star system within decades. This demonstrates that light's memory has physical consequences beyond information transfer. The momentum memory can do work, can change the motion of objects, can propel spacecraft across interplanetary or even interstellar distances. Photons are not just passive carriers of data. They are active participants in physical processes, transferring energy and momentum while preserving information about sources and interactions. Photosynthesis and biological light memory. Finally, consider how living organisms use light's memory. Photosynthesis is perhaps the most important light-driven process on Earth, converting sunlight into chemical energy that powers nearly all terrestrial ecosystems. Plants, algae, and photosynthetic bacteria capture photons from the sun and use their energy to synthesize sugars from carbon dioxide and water. The photons carry energy and information about the sun's spectrum, and this information is read and processed by biological molecules with extraordinary efficiency. The process begins when a photon strikes a chlorophyll molecule in a plant cell. The energy from the photon excites an electron in the chlorophyll to a higher energy state. This excited electron is then transferred through a series of molecules in a process called the electron transport chain, ultimately driving the synthesis of ATP, the energy currency of living cells. The electron's journey converts light energy into chemical energy stored in molecular bonds. What is remarkable is the efficiency. Photosynthesis operates at nearly 100% quantum efficiency, meaning almost every photon absorbed triggers an electron transfer. This is extraordinary because biological systems are warm, wet, and noisy environments where quantum coherence normally decays in femtoseconds. Yet photosynthetic systems maintain coherence long enough to transfer energy and electrons with minimal loss. Recent research suggests that quantum coherence plays a role in photosynthesis's efficiency. When a photon is absorbed by a light-harvesting complex, the excitation energy does not follow a single path to the reaction center. Instead, it exists in a quantum superposition of multiple paths simultaneously, exploring all possibilities at once and finding the most efficient route. This quantum search happens in picoseconds. Faster than decoherence can destroy the superposition. The photons that drive photosynthesis carry memory from the sun 8 minutes old. They preserve information about the solar spectrum, the temperature of the sun's photosphere, the energy available for biological use. Plants have evolved to read this memory, to extract energy and information from sunlight with efficiency that rivals the best human technology. Every leaf is a light detector, every chloroplast a quantum device processing photon memory to power life. This biological use of light's memory connects the cosmic to the terrestrial, the physical to the living. The same photons that astronomers study to understand distant stars are captured by plants to build sugars. The same quantum mechanics that describes interference and entanglement governs energy transfer in photosynthetic complexes. Light's memory serves both understanding and survival, both knowledge and sustenance. We are, in a very real sense, beings made of captured sunlight. The carbon in our bodies came from plants that synthesized it using photon energy. The energy that powers our metabolism comes from breaking down molecules that plants built using light. Every calorie we consume traces back to photons from the sun, absorbed by photosynthetic organisms and converted into chemical form. We are walking repositories of light's memory, our very existence dependent on photons that carried energy from nuclear fusion in the solar core to biological molecules on Earth's surface. Human consciousness is limited. We experience only a tiny sliver of the electromagnetic spectrum, seeing wavelengths from about 380 to 700 nanometers, a narrow band we call visible light. The universe emits radiation across a vast range, from radio waves meters long to gamma rays smaller than atomic nuclei. Each photon at each wavelength carries information, preserves memories of events and processes. But we are blind to most of it, aware only of the thin slice our eyes evolved to detect. Consider what we miss. Radio waves from space carry information about cool gas clouds, pulsars, and active galactic nuclei. Infrared light reveals heat signatures, dust-enshrouded stars, and the cosmic microwave background. Ultraviolet light shows hot stars and energetic processes. X-rays and gamma rays trace the most violent events in the cosmos: supernovae, black hole accretion, neutron star collisions. Each wavelength regime provides a different view of the universe, revealing phenomena invisible at other wavelengths. Light remembers all of this. Every photon at every wavelength carries memory of its source, preserving information that exists whether or not anyone observes it. The universe is filled with memories we cannot access directly, information preserved in electromagnetic radiation outside our narrow sensory range. Only through instruments, through devices that detect photons we cannot see and convert their information into forms we can perceive, do we gain access to this hidden memory. But even with instruments, we miss most of what light remembers. Every second, countless photons from countless sources pass through Earth without being detected. They carry memories of distant stars, ancient galaxies, exotic objects we have not yet discovered or imagined. These memories simply pass by, information traveling through space, preserved perfectly in photon quantum states, but unread, unobserved, unknown. There is something humbling about this. The universe preserves information with perfect fidelity, maintaining a complete record of cosmic history encoded in light fields that fill all of space. Yet we access only an infinitesimal fraction of this record. We are surrounded by memories we cannot read, immersed in information we cannot access, living within a vast archive of cosmic knowledge that remains almost entirely closed to us. This raises questions about the nature of memory itself. If information is preserved in unobserved photons, does it matter? If light carries memories that no one will ever read, are those memories meaningful? Or is memory inherently relational, requiring not just preservation of information but also a reader to decode it, an observer to give it meaning? Perhaps the universe does not care. Light preserves information because that is what light does. Photons travel through space because that is what photons do. The quantum states evolve deterministically because that is how quantum mechanics works. None of this requires purpose or meaning. It simply is the natural consequence of physical law operating in a universe where electromagnetic fields and charged particles exist. Yet we, as conscious observers, cannot help but ascribe meaning. When we detect ancient photons from the cosmic microwave background, we do not merely measure temperature fluctuations. We see the seeds of galaxies, the birth of structure, the infancy of the universe itself. We read memory and extract meaning, constructing narratives about cosmic history, scientific theories about how the universe evolved, philosophical reflections on our place in the vastness of space and time. Light provides the raw material for this meaning-making. The photons do not know or care what information they carry. They simply preserve correlations between physical states, maintaining connections between distant events. But when consciousness intercepts these photons, when human minds decode the information they carry, meaning emerges. The objective physical memory becomes subjective experiential memory. Raw data becomes understanding. Preserved correlations become known history. This is perhaps light's ultimate gift. Not just that it preserves information, but that it makes information accessible across cosmic distances and timescales, allowing consciousness to learn, to discover, to understand reality beyond the immediate present and immediate location. Light's memory enables science, enables knowledge of the universe, enables the peculiar situation where matter arranged as conscious beings can study its own origins and contemplate its own nature. From a photon's perspective, if we can imagine such a thing, the universe is profoundly different from our experience. Time does not pass. Distance has no meaning. The moment of emission and the moment of absorption are the same moment. The photon is created and destroyed in a single timeless instant, With everything in between, the vast journey, the billions of years, the crossing of cosmic voids experienced as nothing, as zero duration, as an absence of interval. What does this mean? It means that from the photon's reference frame, it does not experience traveling. It does not experience waiting. It does not experience existing between emission and absorption. For the photon, there is only the moment of interaction at the beginning and the moment of interaction at the end, with no between in any experiential sense. This suggests a strange kind of loneliness, though not one the photon could experience since experience requires time. The photon is disconnected from the universe in a fundamental way. While matter experiences time, ages, changes, evolves, the photon exists in an eternal instant. It is forever frozen at the moment of its creation, never aging, never changing internally, simply propagating through space at the speed of causality until it interacts and ceases to exist. Yet photons connect the universe. They create causal links between distant events. They carry information from one location to another. They enable communication across vast distances. The photon is simultaneously isolated in its own timeless reference frame and deeply connected to the broader structure of spacetime through the causal relationships it creates. This duality, isolation and connection, timelessness and causality, is at the heart of light's nature. Photons are strangers to time, yet they define time's arrow through the one-way flow of information from past to future. They experience nothing, yet they enable all observation and knowledge. They exist in a realm where distinctions between past and present collapse, yet they are the primary means by which conscious beings distinguish past from present. There is something almost tragic about this. Light remembers perfectly, yet it cannot know what it remembers. It preserves information across billions of years, yet those years do not exist in its experience. Connects everything, yet it is connected to nothing. The photon is the ultimate messenger, carrying messages it cannot read, delivering information it cannot comprehend, serving a purpose it cannot understand. Or perhaps this is the wrong way to think about it. Perhaps photons are not lonely but liberated. Unbound by time, unencumbered by mass, traveling always at the maximum speed allowed by physics, photons are in some sense the freest things in existence. They are pure motion, pure energy, pure information propagating through space-time with absolute simplicity and elegance. Human consciousness, bound to matter, trapped in the flow of time, experiencing entropy and aging and decay, might look at the timeless existence of photons with envy. We are weighed down by mass, slowed by inertia, constrained by causality to experience only the present moment as it slides inexorably from past to future. Photons transcend all of this, existing simultaneously at emission and absorption, free from temporal flow, immune to aging and entropy. But we have something photons lack. We have experience. We have memory in the subjective sense, the felt experience of remembering, of knowing we once knew something different, of recognizing change. Photons preserve information but have no awareness of preservation. They connect events but have no experience of connection. They are memory without remembering, information without knowledge, connection without relationship. Perhaps this is the ultimate distinction between physical memory and conscious memory. Physical memory, like that carried by photons, is objective, perfect, eternal within its domain. Conscious memory is subjective, imperfect, transient. But conscious memory has something that physical memory forever lacks. It has meaning. It has the felt quality of remembrance, the recognition of past and present, the awareness of being a being that exists across time and carries its history within itself. Light's memory enables our memory. Photons deliver information that our brains encode as neural patterns, creating the substrate for conscious recall. But the conscious experience of remembering is something entirely different from the physical preservation of information in photon states. One is objective and measurable, the other subjective and experiential. Both are real, both are important, but they are not the same thing. Let us journey now to the end of time, to the ultimate fate of the universe in the current understanding of cosmology. If the universe continues to expand forever, as evidence strongly suggests, it will eventually reach a state called heat death, where all useful energy has been dissipated, All stars have burned out. All black holes have evaporated, and nothing remains but a cold, dark, nearly empty void. In this far future, perhaps 10 to the power of 100 years from now, give or take a few orders of magnitude, the universe will be unimaginably different from what we see today. Galaxies will have spread so far apart that each will be isolated, unable to see any others beyond its own gravitationally bound members. Stars will have exhausted their fuel, ending as white dwarfs, neutron stars, or black holes. Planets will have drifted away from dead stars or fallen into them. Even black holes will have evaporated through Hawking radiation, leaving nothing but photons and a few particles scattered across expanding space. But photons will remain. They will be the last survivors, the final witnesses to a universe that has died. Stretched to impossibly long wavelengths by the expansion of space, carrying vanishingly little energy, these photons will still preserve memories of the ancient universe. They will remember stars that burned trillions of years ago. They will carry information about galaxies that formed and dispersed before heat death arrived. They will be the last physical records of a cosmos that once teemed with structure and complexity. Yet there will be no one to read these memories. No stars remain to create observers. No planets remain to harbor life. No structures remain complex enough to support consciousness. The photons will travel forever through expanding emptiness, carrying memories that will never be accessed, preserving information that will never be decoded, witnessing a universe that has forgotten itself. Is this the ultimate tragedy? That light remembers perfectly, eternally, yet at the end of time, all that memory becomes meaningless because there is no one left to read it? Or is there some consolation in knowing that the memory persists, that information is not lost even when all observers have vanished, that the universe's history remains encoded in the photons forever traveling through the void? Perhaps in the final analysis, it does not matter. Memory, meaning, significance, these are concepts that only apply when consciousness exists to apply them. In a universe with no observers, information may persist, but it has no meaning because there is no one to interpret it. The photons will travel. Their quantum states will evolve. The correlations they preserve will remain perfect. But without consciousness to read memory, to extract information, to construct meaning, it is as if the memory does not exist at all. Or perhaps we are thinking about this wrong. Perhaps meaning is not something added to information by observers. Perhaps information itself is meaningful, objectively and intrinsically, whether or not anyone ever decodes it. Perhaps the fact that correlations persist, that past events remain connected to present states through physical continuity, is meaningful in itself, independent of consciousness. This is a deep question without a clear answer. What we can say is that light's memory will outlast everything else. Stars will die, galaxies will disperse, black holes will evaporate, but photons will remain, traveling through an ever-expanding universe, carrying memories of a cosmos that once was. They will be the last keepers of cosmic history, faithful to the end even when there is no one left to appreciate their faithfulness. In a way, this is fitting. Light has been the universe's memory from the beginning. The cosmic microwave background photons carry information from just 380,000 years after the Big Bang. Starlight carries memories of stellar evolution across billions of years. In the end, when all else has faded, light will still be there, still preserving, still remembering, still connecting past to present even when present has become an empty void. Perhaps future civilizations, if such things are possible, might find ways to persist even in the heat-death universe. They might harvest the last available energy, encode themselves in structures we cannot imagine, find ways to think and remember even as the cosmos grows cold and dark around them. If they do, they will still depend on light's memory, on photons that carry information across vast distances, that preserve correlations that might otherwise be lost to entropy and time. Or perhaps consciousness will discover that it can exist in forms that do not require matter, that thought itself can persist as patterns in fields or information encoded in the geometry of spacetime itself. In such a scenario, light's memory might become the substrate for conscious memory, photons carrying not just physical information but the very essence of thought and awareness across cosmic distances and timescales. These are speculations far beyond what current science can address. but they point to something important. Light's memory is more than a curiosity. It is fundamental to how the universe preserves and propagates information. It connects the past to the present and the present to the future. It enables knowledge, enables observation, enables consciousness to exist in a form that can understand reality beyond the immediate here and now. Without light's memory, we would be blind to the cosmos. We would know nothing of stars, galaxies, cosmic history. We would be trapped in our immediate location, unable to see, unable to learn, unable to construct theories about the larger universe we inhabit. Light's memory is what lifts consciousness beyond the local and momentary, allowing minds to range across space and time, to learn about distant places and ancient events, to understand a universe vastly larger than any single observer could ever directly experience. Let us journey now to the end of time, to the ultimate fate of the universe in the current understanding of cosmology. If the universe continues to expand forever, as evidence strongly suggests, it will eventually reach a state called heat death, where all useful energy has been dissipated, all stars have burned out, all black holes have evaporated, and nothing remains but a cold, dark, nearly empty void. In this far future, perhaps 10 to the power of 100 years from now, give or take a few orders of magnitude, the universe will be unimaginably different from what we see today. Galaxies will have spread so far apart that each will be isolated, unable to see any others beyond its own gravitationally bound members. Stars will have exhausted their fuel, ending as white dwarfs, neutron stars, or black holes. Planets will have drifted away from dead stars or fallen into them. Even black holes will have evaporated through Hawking radiation, leaving nothing but photons and a few particles scattered across expanding space. But photons will remain. They will be the last survivors, the final witnesses to a universe that has died. Stretched to impossibly long wavelengths by the expansion of space, carrying vanishingly little energy, these photons will still preserve memories of the ancient universe. They will remember stars that burned trillions of years ago. They will carry information about galaxies that formed and dispersed before heat death arrived. They will be the last physical records of a cosmos that once teemed with structure and complexity. Yet there will be no one to read these memories. No stars remain to create observers. No planets remain to harbor life. No structures remain complex enough to support consciousness. The photons will travel forever through expanding emptiness, carrying memories that will never be accessed, preserving information that will never be decoded, witnessing a universe that has forgotten itself. But perhaps this picture of the far future is incomplete. In an eternal, expanding universe, quantum fluctuations never stop. Given infinite time, any configuration of matter that is physically possible will eventually occur somewhere, no matter how unlikely. This includes complex structures like human brains, spontaneously assembled by random fluctuations from the quantum vacuum. These hypothetical entities are called Boltzmann brains, named after physicist Ludwig Boltzmann, who explored similar ideas about entropy and thermodynamics. A Boltzmann brain would be a disembodied consciousness that pops into existence complete with memories, thoughts, and sensations, persisting for a brief moment before dissolving back into chaos. It would have no history, no past beyond the false memories it was created with, no future beyond a few subjective moments. If Boltzmann brains can form, they will vastly outnumber ordinary observers like us who evolved through biological processes. Evolution requires low entropy initial conditions and billions of years of stellar and planetary development. Boltzmann brains require only quantum fluctuations and infinite time. In the far future, when all ordinary structure has decayed, Boltzmann brains might be the only form of consciousness remaining in the universe. This raises a disturbing question. If most observers are Boltzmann brains with false memories rather than evolved beings with real histories, how do we know we are not Boltzmann brains ourselves? The memories we have of the past, the evidence we see for billions of years of cosmic and biological evolution, could all be illusions, fabricated patterns imposed on a momentary fluctuation that will dissolve back into noise in the next instant. Light's memory does not resolve this paradox. A Boltzmann brain could include memories of observing starlight, complete with detailed knowledge of astronomy and physics. These memories would be false, encoding information about stars and galaxies that never existed. The photons the Boltzmann brain believes it observes might themselves be part of the fluctuation. Quantum fields arranged to create the illusion of electromagnetic radiation carrying information from distant sources. Yet there is something unsatisfying about this scenario. If we are Boltzmann brains, our memories and observations are meaningless. The universe we think we see does not exist. The photons we believe carry information about cosmic history carry nothing because there is no history, only a random fluctuation that will vanish in the next moment. This seems to violate the principle of mediocrity, the idea that we should not assume we occupy a special or unusual position in the universe. Most physicists believe we are not Boltzmann brains, that the universe genuinely has the low-entropy initial conditions and long history that observations suggest. But the Boltzmann brain paradox reminds us that light's memory, while reliable in principle, rests on assumptions about the nature of reality that we cannot prove with absolute certainty. We trust that photons preserve information about real past events rather than being part of an elaborate illusion because any alternative seems to lead to solipsism and meaninglessness. Perhaps the resolution is that consciousness requires continuity, that genuine observers must persist long enough to accumulate memories and make observations over time. Boltzmann brains, if they exist, would be momentary fluctuations lacking the temporal extent necessary for real thought and experience. The fact that we experience time passing, that we remember a coherent history rather than random noise, suggests we are not Boltzmann brains but evolved creatures with genuine pasts. Light's memory supports this. The photons we observe show consistent patterns across vast distances and timescales, creating a coherent picture of cosmic evolution. If we were Boltzmann brains, we would expect to see random or contradictory data rather than the lawful behavior that light exhibits. The reliability of light's memory argues against the Boltzmann brain scenario, suggesting that the universe is real, history is real, and the information carried by photons genuinely connects us to distant events rather than being elaborate noise. Another philosophical possibility is that the universe is a simulation, a computational process running on some substrate beyond our ability to observe directly. If true, photons would not be fundamental entities but computational constructs, information structures in a digital universe designed to behave as if they were massless particles carrying electromagnetic radiation. In a simulated universe, light's memory would be implemented through data storage in whatever computer runs the simulation. The photon's quantum state would be a set of variables in memory, updated according to algorithms that implement the laws of physics. When we observe light, we would be reading computed data rather than physical properties, though the distinction might be meaningless if the computation is sufficiently detailed. The simulation hypothesis is unfalsifiable in principle. Any evidence that seems to disprove it could be explained as part of the simulation's design. Any inconsistency we might discover could be a computational artifact, a rounding error or resource limitation in the simulation's implementation. We cannot prove we are not living in a simulation because any such proof would itself be part of the simulation. Yet the hypothesis raises interesting questions about light's memory. If the universe is simulated, is information really preserved across space and time? Or is it computed on demand when observers make measurements? Perhaps the photons traveling between stars do not exist, except when something observes them. Their properties calculated only when needed to match what an observer would expect to see. This would be consistent with quantum mechanics, which holds that properties do not have definite values until measured. In a simulation optimized for computational efficiency, it would make sense to avoid calculating unnecessary details. The photons from distant stars need not be continuously simulated during their journey. The simulation need only ensure that when an observer finally detects them, the photons have properties consistent with having traveled from the source according to physical law. But if this is true, is light's memory real? Is information genuinely preserved in photon quantum states? Or is it reconstructed retroactively when observations occur? The question might be meaningless because real and simulated are identical if the simulation is perfect. A photon in a simulated universe behaves exactly like a photon in a physical universe by design. The information it carries is just as reliable, just as faithful to the source, just as useful for constructing knowledge about the simulated cosmos. Perhaps the lesson is that information is more fundamental than physical substance. Whether photons are elementary particles or computational constructs, they serve the same function. They preserve correlations between events, enable communication across distance, support the existence of observers who can learn about reality beyond their immediate location. The substrate does not matter. What matters is the pattern, the information, the memory encoded in whatever entities play the role of photons in the structure of reality. In this view, light's memory is real regardless of whether the universe is simulated or physical. Information is preserved. Correlations connect past to present. Observations reveal consistent patterns that enable understanding. Whether these patterns exist in quantum fields or computer memory is a question about ontology, about what reality is made of. But functionally, operationally, experimentally, the answer does not change how light behaves or what information it carries. We are back to epistemology, to questions about what we can know and how we know it. Light's memory is our primary tool for knowing anything beyond the immediate present and immediate location. Whether light is fundamental or derived, physical or computational, does not change its role as the carrier of information that enables knowledge. We trust light because it is reliable, because it preserves information faithfully, because observations of light create consistent pictures of reality that allow prediction and understanding. One final philosophical puzzle involves black holes and the fate of information. According to classical general relativity, anything that falls into a black hole is lost forever, crushed to infinite density at the singularity. No information can escape because nothing, not even light, can escape from inside the event horizon. This seems to violate quantum mechanics, which requires that information be conserved, never truly destroyed even when systems become highly disordered. Stephen Hawking discovered that black holes are not entirely black. They emit thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly evaporate. Given enough time, a black hole will evaporate completely, leaving only the Hawking radiation behind. But here is the paradox. Hawking radiation is thermal, meaning it appears to carry no information about what fell into the black hole. If you drop a book and a lump of coal with the same mass into a black hole, the Hawking radiation would be identical in both cases. The information about what was dropped seems to be destroyed, violating the principle that information is conserved in quantum mechanics. This paradox has occupied theoretical physicists for decades. Various solutions have been proposed. Some involve information being encoded in subtle correlations in the Hawking radiation that appear thermal but actually preserve information in ways we do not yet understand. Others involve information being stored at the event horizon, spread across the black hole's surface in holographic form. Still others suggest modifications to quantum mechanics or general relativity that prevent information loss. Light plays a central role in this debate because Hawking radiation is primarily electromagnetic, photons carrying energy and entropy away from the black hole. If information is preserved, it must be encoded in these photons somehow, perhaps in correlations between photons that look random when examined individually but reveal structure when analyzed collectively. The black hole information paradox reveals limits to our understanding of how light preserves memory in extreme conditions. In most circumstances, photons faithfully carry information from source to observer. But near event horizons, where gravity becomes extreme and spacetime curvature approaches singularities, our theories break down. We do not know if information is truly preserved, how it might be encoded, or what happens to photon memory when light interacts with black hole horizons. This uncertainty is humbling. For all our knowledge about light and information, there remain fundamental questions we cannot answer. Does information survive black hole evaporation? Can photons preserve memory even when spacetime itself becomes pathological? Are there limits to information preservation beyond which even light cannot carry accurate memory? These questions remain open. They challenge our deepest assumptions about the nature of reality, about whether information is truly fundamental, about the ultimate fate of memory in a universe with black holes. Light, our most reliable carrier of information across cosmic distances, might encounter limits we have not yet discovered, boundaries where memory fails and information is genuinely lost despite quantum mechanics' insistence on conservation. Or perhaps information is never lost, merely scrambled in ways so complex that extraction becomes impossible in practice, even if possible in principle. Perhaps the photons emitted by black holes carry complete information about everything that ever fell in, encoded in correlations so subtle that no conceivable measurement could decode them. Memory would persist, but access would be denied by computational limitations rather than physical law. We do not know. This ignorance is itself important. It reminds us that light's memory, while extraordinary, operates within a universe whose fundamental nature remains partially mysterious. We trust light to carry information reliably because it has never failed us in all the circumstances we can test. But there may be regimes where trust must give way to uncertainty, where memory encounters boundaries we have not yet mapped. We return now to our central question. How does light, massless and eternal from its own perspective, carry the weight of memory? How does nothing weigh everything? The answer, as we have discovered, is that memory is not mass. Information is not matter. What light carries is correlation, the relationship between events, the connection between past and present. A photon's quantum state encodes properties of the source that emitted it, creating a physical link across space and time. This link has no mass, no weight in the conventional sense. But it has reality. It has consequence. It enables effects that would be impossible without it. When we observe a distant star, we are connected to that star through photons that have traveled light years to reach us. The connection is real even though nothing physical moved from the star to us except massless radiation. Information moved, correlation moved, memory moved. The photon that enters our eye causes neural activity that reconstructs in our mind's eye an image of the distant star. We see across cosmic distances because light carried correlation faithfully, preserving information through its quantum state, delivering memory from there to here, from then to now. This is the weight of light. Not mass, not force, but consequence. Light shapes our understanding of reality. It determines what we can know about the universe. It defines the limits of observation and enables everything within those limits. The weight of light is the weight of knowledge, of connection, of memory made physically real through the propagation of massless particles across spacetime. In a universe without light, consciousness would be profoundly limited. We would be aware only of what we could touch, what we could sense through direct physical contact. The cosmos beyond our immediate location would be unknown and unknowable. We could not see, could not observe, could not learn about anything distant or ancient. Our knowledge would be constrained to the here and now, unable to extend across space or back through time. Light liberates consciousness from this constraint. It allows awareness to expand beyond the body, beyond the planet, beyond the galaxy, reaching across billions of light years to observe the structure of the universe itself. This reach is possible because photons carry memory, because information encoded in quantum states can propagate across cosmic distances without degradation, because light preserves correlations that conscious minds can decode and understand. The weight of light is thus the weight of possibility. It is what allows knowledge to exist, what makes science possible, what connects isolated conscious beings to the larger universe. Without light's memory, we would be alone, trapped in darkness, unable to see the stars or understand our place in the cosmic story. With light's memory, we become participants in that story, observers who can read cosmic history, learners who can discover physical law, minds that can contemplate reality at scales far beyond our physical size or temporal duration. Light has witnessed everything. Every event in cosmic history since the universe became transparent has been accompanied by photons, radiation that carries memory of what happened. The birth of stars, the explosion of supernovae, the collision of galaxies, the formation of planets, the emergence of life, all of it has been illuminated, all of it has generated photons that preserve information about those events. Some of those photons have been absorbed, their memory transferred to other systems. Some continue traveling, carrying information through space, waiting to be observed. Every photon in existence is a witness to some event, however small or large. The photon from our sun carries memory of the solar surface 8 minutes ago. The photon from a distant galaxy carries memory of conditions billions of years in the past. The cosmic microwave background photon carries memory of the universe when it was 380,000 years old. Light does not choose what to remember. It does not select important events over trivial ones. It simply preserves information about whatever physical process created it. The photon from a supernova explosion is no more special, from the photon's perspective, than the photon from a candle flame. Both carry memory encoded in quantum states. Both travel at the speed of light, experiencing no passage of time. Both preserve information with perfect fidelity until they interact with matter and are absorbed. Yet we distinguish between these memories based on what we find meaningful. We build telescopes to capture photons from distant supernovae, studying their light to understand cosmic expansion and stellar evolution. We rarely bother to study the light from candles, except as examples in physics classes or artistic subjects for photography. The photons care nothing for this distinction, but we care deeply because we are the ones who assign meaning to information, who decide what memories matter and what can be ignored. This points to a fundamental truth. Memory is meaningless without remembering. Information is useless without interpretation. Light preserves and transmits, but it does not understand or care. Understanding and caring require consciousness, require minds that can decode information and extract meaning, that can place memories in context and construct narratives about reality. We are the ones who give weight to light's memory. We are the ones who read cosmic history in ancient photons. We are the ones who find meaning in the information that light carries. The photons simply do what photons do, traveling through space, preserving correlations, connecting events. But when consciousness intercepts them, when minds decode their quantum states and extract information, memory becomes knowledge and information becomes understanding. In this sense, we participate in light's witnessing. We are not passive receivers of information but active interpreters who construct meaning from physical states. When we observe a distant galaxy, we are completing a process that began billions of years ago when photons left that galaxy. The photons traveled faithfully, preserving information through the journey. But the information only becomes knowledge when we observe it, when our instruments detect the photons and our minds interpret the data. Light and consciousness together create the phenomenon of cosmic knowledge. Light provides memory, consciousness provides meaning. Light preserves information, consciousness interprets it. Light connects events across space and time. Consciousness recognizes those connections and builds understanding from them. Neither can do alone what they accomplish together. As we near the end of this journey, we confront a final meditation. Everything is temporary. Stars burn out. Galaxies disperse. Even the universe itself may eventually fade into cold, dark emptiness. Light's memory persists longer than anything else, but even light will eventually be stretched by cosmic expansion to wavelengths so long that it carries vanishingly little energy and becomes nearly undetectable. There is something melancholy about this. All the beauty we observe, all the structure and complexity, all the stars and galaxies and potential civilizations will eventually end. The universe is dying slowly, and there seems to be no escape from heat death if expansion continues forever. Light will remain as the last witness, but eventually even light's memory will fade into insignificance as photons are redshifted into oblivion. But perhaps we should find comfort rather than sadness in impermanence. Nothing lasts forever, and this includes suffering, loneliness, and ignorance. The universe is constantly changing, constantly creating new structures, new patterns, new possibilities. While stars die, new stars form. While galaxies drift apart, within each galaxy new solar systems are born. While individual consciousnesses end, new consciousnesses emerge. Light's memory connects these transient phenomena, creating continuity in a universe of change. The photon from an ancient galaxy carries information about conditions billions of years ago, linking that distant past to our present. The photon from our sun connects solar processes to human perception. The photon from the cosmic microwave background links the infant universe to observers living near the end of cosmic history. This continuity through change is perhaps the deeper lesson. Nothing is permanent, but nothing is completely lost either. Information persists. Memory survives. Light carries correlations forward through time, ensuring that past influences present even as everything transforms. The universe has no permanent structures, but it has permanent relationships, causal connections that span space and time, patterns of information preserved in the propagation of light and other fields. We are part of this pattern. Our existence is temporary, our consciousness brief and fragile. But we are connected through light to a larger cosmos, participants in processes that extend far beyond our individual lives. When we observe distant stars, we receive photons that traveled for centuries or millennia. When future observers look toward our sun, they will receive photons carrying information about our time, our world, perhaps even indirect evidence of our civilization. Light ensures that nothing is completely forgotten, at least not immediately. Information propagates outward at the speed of light, creating an expanding sphere of memory. This memory may not be accessible forever, but while it persists, it connects past to present and present to future in an unbroken chain of causality. Perhaps this is enough. Perhaps we do not need permanence. Perhaps it is sufficient to know that while we exist, we are connected to something larger than ourselves, part of a cosmos that preserves information and enables understanding. Light's memory gives us access to cosmic history and ensures that our present will become part of history for future observers. We are temporary, but we are not isolated. We are transient, but we are not meaningless. As this documentary draws to a close, as your consciousness drifts towards sleep, consider the photons passing through this room. They carry memories. Some come from the sun, preserving information about solar processes from 8 minutes ago. Some come from stars, carrying memories decades or centuries old. Some might be cosmic microwave background photons, ancient witnesses to the infant universe, older than planets and stars and galaxies. These photons surround you, pass through you, interact with the atoms of your body in tiny ways that mostly go unnoticed. Each photon is a messenger carrying information across space and time. Most will pass by without being observed, their memories unread, their information unaccessed. But some will be absorbed by your eyes, by instruments, by matter that preserves the information in new forms. You are immersed in memory. The light filling this space is not just illumination. It is information, correlation, connection between distant events and present observation. You are surrounded by the past preserved in photons, by messages sent from far away and long ago, traveling at the speed of causality to reach you now. And you, in turn, are sending messages. Your body radiates infrared light, photons that carry information about your temperature, your chemical composition, your presence in this place at this time. These photons will travel outward, most escaping into space, some being absorbed nearby. They will carry memory of you beyond your immediate location, beyond your immediate time. In some small way, you are contributing to the universe's archive of information, adding your photons to the cosmic collection of memories. Light connects everything. It carries information from stars to observers, from past to present, from source to detector. It creates the possibility of knowledge, of understanding, of conscious awareness extending beyond the immediate here and now. Without light's memory, the universe would be a collection of isolated moments, disconnected events, information trapped in local regions with no way to propagate or persist. With light's memory, the universe becomes a coherent whole, a structure where distant parts remain connected, where past influence is present, where information can survive across cosmic distances and timescales. This coherence is what makes science possible, makes astronomy possible, makes it possible for consciousness to understand its place in a cosmos vastly larger than any single mind could experience directly. As you drift toward sleep, as consciousness fades and memory becomes dream, remember that you are part of this larger pattern. You are connected through light to distant stars and ancient photons. You are a receiver of cosmic messages, an interpreter of information that has traveled across the void to reach you. And you are a sender, radiating your own photons, contributing your own information to the universe's ongoing story. Light remembers what consciousness forgets. Light preserves what time erodes. Light connects what space separates. The weight of light is the weight of memory, the burden and gift of information preserved across cosmic expanses, delivered faithfully by massless messengers that transcend time in their own reference frames while defining time's arrow for everything else. You are surrounded by memory. You are immersed in information. You are connected through light to a universe that remembers, that preserves, that maintains continuity through change. And as consciousness fades into sleep, as awareness dissolves into dreams, light continues its work, carrying memories through the darkness, preserving information across the night, connecting all things through the simple, elegant, eternal propagation of massless particles at the maximum speed allowed by physics. The photons travel, the memories persist, the universe remembers, and we briefly, gloriously, impossibly get to participate in that remembering, reading light's eternal witness, understanding through consciousness what light preserves through physics. Rest now. Light will continue its journey. Memory will persist. And when consciousness returns, the photons will still be there, carrying their ancient messages, waiting to be read, waiting to connect you once again to the vast cosmos that exists beyond this room, beyond this moment, beyond this brief span of awareness we call a lifetime. The universe remembers. Light never forgets. And we, for now, get to know what light knows, to see what light preserves, to understand what light connects across the infinite expanse of space and the infinite flow of time. Sleep well. The memories are safe. The photons will carry them through the darkness and deliver them, faithfully, eternally, when consciousness awakens to read them once more.